All right, well, in section 6.5, we were talking about least squares problems. So the idea is that sometimes you cannot solve a system of equations. There is not a solution formally to a system of equations. And we understand, we learn geometrically what that means. Essentially, there's no linear combination of the column vectors of a matrix A that would equal the well, like look in theorem 15. You have this A times X equals B, right? That's what you're trying to solve. But if there's no linear combination of the column vectors of A that will equal the vector B, then you have no solution vector X. And essentially, this means that the vector B is not in the column space of the matrix A. So what we endeavor to do then is try to make A times X as close to vector B as possible. In other words, A times X on the left there is, in the matrix equation, AX equals B. A times X is a vector on the left, and B is a vector on the right. So we want those vectors as close as possible, and that means the distance between them is as small as possible. And so to find that, we need to find the least squares solution. And that's what we actually have a formula. If the matrix A is invertible, we learn that there is a formula to find that least squares solution, X hat. And if the matrix A is not invertible, then you have to solve a system of equations based on the normal equations, which is A transpose A times X equals A transpose times B. And but what happens is, of course, you end up getting an infinite number of least squares solutions, and that's really never desirable. At least I've not seen it in my work that it's desirable. We like one unique least squares solution. And so basically, if the matrix A is containing, if it contains, like for instance, information, data on different individuals, we'd like all the individuals to be different in some aspect, so that you have linearly independence of the columns of the matrix A. Now, in this theorem 15, they show you yet another way to find the least square solutions X hat, and this has to do with the QR factorization that you learned back in section 6.4 when you studied the Graham-Schmidt process. A matrix A can be written as it can be factored as a matrix Q whose columns are orthonormal basis for the column space of A, and then R is an upper triangular invertible matrix. And it turns out that X hat will equal R inverse times Q transpose times B. And to prove this, what they do is, here's a portion of the proof. You have A times X hat, but if A then is Q times R, the matrix Q can be, hold on here. So yeah, if X hat equals R inverse times Q transpose times B, we can put that in. Okay, so let me rephrase it a new way. Here, let me sort of. So A equals Q times R, that's the QR factorization. So AX hat equals QR times X hat. Now, what if X hat were equal to R inverse times Q transpose times B? That's what they're suggesting up here in theorem 15. What if that's the case? Well, then we replace X hat with R inverse times Q transpose times B, and we get this expression. But R and R inverse, for the product is the identity, so that's going to get us Q transpose times Q times B. Okay. But keep in mind the columns of Q form an orthonormal basis for the column space of A. And you learned in Theorem 10, and Theorem 10 was back in section 6.3, that Q transpose, Q times Q transpose times B, sorry, Q times Q transpose times a vector B is the orthogonal projection of the vector B hat on, well, it's the orthogonal projection of the vector B onto the column space of A. Okay, and therefore A times X hat would equal B hat. And so the linear combination of the column vectors of A, the matrix A, that give you the projection vector, that linear combination forms your least squares solution. So it's really quite an amazing result. And one thing that the book mentions, it talks about it always has these numerical notes. And they comment that in terms of like, well, in Theorem 15, you're computing well, let me go up here. In Theorem 15, X hat is found by R inverse times Q transpose times B. But that's not the only way you can find X hat. You can multiply both sides of that equation 6 by R on the left. And then you're going to get what they show you in the numerical note. You're going to get that Rx times equals Q transpose times B. And they comment that it's much faster to solve this problem, this set of equations in 7, by back substitution or row operations than to compute R inverse. Because anytime you have to compute R inverse, it can be computer intensive for a computer. It can take time. And again, you might think about what you had to do when you had to compute the inverse of a 3 by 3 matrix by hand. You were tested on that earlier in the semester. That took some time, right? Well, if it takes you time, it's going to take a computer time also. And remember, the matrix R is an upper triangular matrix on the left. So in that equation 7, in the numerical note, equation R is an upper triangular matrix. So that means there's a lot of zeros. Half of that square matrix, the bottom half is going to be all zeros. And so essentially, solving the system just involves back substitution. In other words, you're in the R times X is in echelon form. And all you have to do is work from the bottom to the top with your row operations to solve for X. And so, you know, these are little things that are helpful. These numerical notes are very helpful. And I actually encourage students to try to take linear algebra because I think it relates very strongly to computer science. You know, so I'd like more. I'm very happy you're in linear algebra. And by the way, I'm teaching that in the fall. So please, if you like my teaching style, I'd be grateful if you recommend me to your friends who have to take linear algebra. You know, I'd be grateful. Okay, are there any questions on that? Okay, well then let's go to this little example here. Let's go to this little example. Example 5, find the least squares solution here for this system. And they do the QR factorization of the matrix A. So that would require using the Gram-Schmidt process for the 3 column vectors of the matrix A. All right, that would be necessary. And then Q transpose times B here is equal to 6, negative 6, 4. And so now you're solving this system. R times X equals Q transpose times B. And you see how easy that is to solve? You see how simple that is? Because the matrix R is upper triangular. Okay, and so that's another way to get your least squares solution. Okay, yeah, Mikhail, that is easy. That is easy. And you know, in math, you're working with fairly small systems of equations, but in applications, well, I mean, you can have a system of equations that have, you can have several hundred equations, and you're solving for several hundred variables. So, you know, it's always nice when we can save computing time. But to save computing time, we have to tell the computer we have to know the theory. We have to know the theory and the concepts in order to come up with algorithms that save computing time. We have to know our linear algebra concepts. And so, all right, very good. Are there any questions before I move on? Okay, very good. Thank you.